Recording underway. So this morning we move into part two of the 4 parts of our course. In part one, we laid a really good foundation for the rest of our course by reviewing some of the major theories in psychology. We certainly did a very thorough job of reviewing research methods that make psychology the scientific study of behavior and mental processes. We also did a pretty thorough job on the biological basis of behavior. So we're going to sort of make the transition into part two of our course by beginning with a section on sensation and perception. And as we move away from sensation this morning into perception next week, that's where we'll start sort of transitioning away from the more heavily biological part of the course into the more psychological part of the course. So we'll get to that in just a bit. In addition to sensation and perception in part two of the course, we will cover consciousness, learning, and memory. And if you ask the supplemental instruction leaders in our course, they'll tell you that learning and memory in particular are the significant chunks of part two of our course. So that's where we're headed. Before we get into some of those details in part two, I do want to take a minute with you guys to review some of the items that caused the most problems on test number 1. So before we get into that, this was the distribution for test number 1. In terms of grades, we had 36% A's and B's if you add those two together. We had 34% D's and F's if you add those two together. So I usually look at that combination. In my mind, that's a +2, right? 36 minus 34. So that's good. There were more A's and B's than there were D's and F's. We had a class average that put us right on the cusp of a C, 72.4, 73. Excuse me, 73 is technically a level for a C. So round that in my mind and say, yeah, that's pretty much a C. What I want to do with you guys is walk through some of the items that caused the most headaches. So as we go through these, if you in your mind think, I think I got that one wrong, that wouldn't be unusual because these are the items that typically, 60% or less of the class got these items correct. So let's run through these together and see if you guys have any questions on them. So this item, number 2 here says, according to the biopsychosocial model, genetic predispositions to the development of depression would be an example of which factor? So we're talking about a genetic vulnerability to something like depression. Is that social? Is that psychological? Is that biological? Which one of those is the right way to go with that question? We're talking about genetic predispositions. Francisco and Alyssa both think it's C, biological. Yeah, they're correct, right? So this is a biological factor that might contribute to something like depression. A little more than half of you guys got that one correct. I've got 6 of these lined up, so let's take a look at all 6 of these. Number 2 on the parade is this one. I'm not even going to read this one because this should look very, very familiar. Why should this look very familiar? Tell me in the chat box. Yeah, this was part of our online session and this exact question. So what's the correct answer here? Yeah, we said it was C, right? This is the one we discussed and said, choice A starts suggesting something causal, and we know that correlation doesn't mean causation. So we said, okay, we could get rid of, A. If we get rid of A, we can get rid of D. What does B say? Factors that lead to poverty. There's nothing here that would suggest that, right? The most conservative kind of summary here without overstepping our bounds as correlational researchers is that these two things are negatively correlated. Okay, so that was, again, right from something we did. I thought I was giving you an easy one there, but only about 55 to 60% of you guys got that one correct. All right, let's see what else we have here on this parade of difficult items. In a neuropsych investigation, a monkey makes an involuntary gesture when a portion of its brain is electrically stimulated. So what part of the brain would you stimulate to make the monkey do an involuntary gesture? Yes, Marissa, the motor strip. Where is the motor strip? Yep. It's going to be the rear portion of that frontal lobe, right? The motor strip at the back of the frontal lobe, sitting adjacent to that somatosensory strip at the front of the parietal lobe. Okay, so that one was C as well. Any questions on that at all? Cool, let's continue on. This one focuses in on your understanding of these different perspectives or theoretical models. Penny is a recovering drug addict. Her treatment program emphasizes the influence of consequences in the environment on her use of her drug of choice. The key word in this question, and this actually was one that a couple people asked me a question about during the test, is about consequences, right? Which one of these perspectives emphasizes consequences as a big shaper of our behavior, right? We do what we do because of rewards and punishments. How people respond to our behavior influences the likelihood of that behavior recurring or not. Yeah, this is behavioral, right? This is a behavioral model where we look at the consequences, and that sounds like that's what's shaping this approach to her treatment. All right? Good, let's keep rolling on here. 2 more to look at together. This one is about a questionnaire about extroversion, which is a stable personality trait. We give the questionnaire, we give it again 6 months later, and we get a correlation of positive 0.10. What does that mean? It's not reliable. It's reasonably reliable. It's not valid. It's reasonably valid. How'd you make sense of this one? About half of you guys or so got this one right. A couple people are suggesting it's not reliable. Why not? If it was reliable, what would this correlation coefficient probably be? Yeah, it's not consistent. It would be a hell of a lot higher, right? The reliability correlation coefficients that we'll get for the good intelligence test that we'll talk about in part 3 of our course, they have test-retest reliability correlation coefficients of like 0.9 and higher. So this is one that's not reliable, especially given that it's a stable personality trait. So it should be consistent from time 1 to time 2, 6 months later. It's not what we're getting. We're getting a scatter plot that looks like it's a mess, and there's no way to discern a pattern here where high scores at time 1 were high scores at time 2, or conversely low scores at time 1 were low scores at time 2. All right. Final item I want to review with you guys is the William James item. This was the worst item on the test in terms of percentage of you getting it right. It was less than a third. I thought this was not a difficult question because William James, is he a structuralist or a functionalist? What is his focus? He's on functionalism. We talked about what's the purpose of behavior. How does it help you, for example, to have memory that works or emotion that works or to be able to plan things out with your frontal lobe, right? So that's a functionalist approach. So which one of these is about the purpose of behavior, right? The adaptive purpose. It's going to be C, right? We've got a question here that says emotions aid in one's adaptation to the environment. What does it get you as a person? How does it benefit you to have these emotions? That's a functionalist kind of perspective on it. So the correct answer again would be C. Any questions on that item or any of these 6 that I pulled up for you guys? All right. Any final comments about test 1? It was too easy. It was too hard. It was fair. It was unfair. It had too much of this. It had too little of that. This is your chance to speak your mind. Hannah thought it was very difficult. A couple other people thought it was fair, fair, fair. Maps pretty nicely onto those learning outcomes. If you look back at the list of learning outcomes from part 1 of the course, you'd be hard pressed to say, I gave you a bunch of questions that had nothing to do with what was on that list. Okay. It definitely had exactly the amount of bio that I said. I counted the items when I gave you that list, so it was exactly what I said it was. No, I think, Ashton, that's about what happens in her environment when she drinks or when she uses drugs, right? How do people respond? That would be something like that. C is 73 to 76. C plus is 77 to 79. So you're asking about this question. With the influence of consequences in the environment on her use of drugs. So this would mean this little phrase here, right? Consequences in the environment on her use. So if she gets lots of attention when she drinks or uses drugs, that might be something that is making it more likely that she's going to drink or use drugs going forward. That make sense? That would be a behavioral account, a behavioral approach to that. Good. So SI is really helpful. I will have some data for you guys regarding folks who did or did not go to supplemental instruction and how they did on test one. I don't have those numbers yet, but when I do, I will certainly share them. So let us turn the page and start moving into part 2 of our course on sensation and perception. Okay, here's the deal. As we talk about sensation and perception, oh, by the way, I forgot to mention, I am going to be out of town next week. I just emailed you guys this announcement, but the announcement is here on Blackboard as well. And so I cannot do a live face-to-face session on Tuesday or a live online session next Thursday. So in place of those class meetings, you've got 2 recordings to look at. Sensation and Perception Part 2 right here is basically the section on perception. It is a recording from a face-to-face class in the fall. And so you'll be able to run through that and basically hear what you would have heard if we had a live face-to-face class. Then next Thursday, I'm still going to be out of town. And I won't be able to get at a computer, do a live online session with you guys. So there's a consciousness recording as well. So basically, the second part of sensation and perception and the section on consciousness are recordings for you here that you can watch at your leisure. Okay, the links were recorded in the email, were included in the email as well. If you want to view them within YouTube itself, you just click on that within it and it'll kick you over into either the Sensation and Perception Part 2 recording or this consciousness recording as well. Okay. All right. And I apologize for missing. I'm actually going to be traveling on the East Coast looking at 2, probably 3 different colleges with my high school senior. So it's just the way things worked out this time around. All right. But the recording make it really useful for me, or it makes they're really helpful to me when I have conferences or other things that keep me from being able to be here for you guys. At least I have the material queued up for you as well. All right, so the section on sensation and perception. Here's how I'm going to try to help you guys get your head around this. The sensation material, which is our focus today, and the perception material, which is in that first of the 2 recordings, are different in this way. Sensation is earlier and more biological processing of incoming inputs from your environment. So you're doing sensation work right now as you listen to my voice, okay? It turns out that the sound waves coming in through your speakers or your earbuds or your headphones, they are being funneled down your auditory canal via the pinna, that is your ear that's hanging on the side of your head. When those sound waves get to the end of that auditory canal, they bang on your eardrum and so on and so forth. And we're going to go through some of those details in the last 15 or 20 minutes today about hearing, okay? When we turn the page and go into that recording on perception, what you're going to notice is it's a lot less biological. So in the sequence of events, perception is a later processing that is more psychological in its focus. What do I mean by that? Well, perception is going to involve things like being able to tell the difference between the meow of a cat and the bark of a dog, and having a mental image, if you will, of a cat or a dog accordingly. So it's going to be less about things going on in your auditory system and hair cells sending messages along and firing action potentials and things being sent on to your auditory cortex and your temporal lobes. That's all sensation. When we get to perception in that first of the 2 recordings for next week, you're going to notice a pretty obvious shift away from biology and more on to psychology. Okay, that's a thing you're going to notice as we make our transition here in this part of the course. All right, so let's lay out a couple of definitions for these terms so we can get ourselves on the same page together. Today's focus, sensation. What is it? It's a process by which sensory organs in your eyes, ears, nose, mouth, skin, and other tissues receive input from your world. Okay, it's database processing in the sense that there's information coming in through your eyes, your ears, etc., and we're doing work with that information. And again, as I talked about this sequentially, this is earlier and more biological in its focus. Okay, how is that different from perception? Well, perception is the organization and interpretation of sensory stimuli by the brain. And I would really focus in on that interpretation piece, right? It's how we make sense of things that we're hearing, things that we're seeing. It's knowledge-based processing in the sense that we're going to learn in that first recording about something called top-down processing, where new encounters that we have with stimuli in our environment are understood based on past experiences, right? This new thing that I'm encountering is similar to, or maybe different from this other thing that I've encountered previously. So again, the way that I think about perception is this is later sequentially, and it's more psychological in terms of how we might characterize it. Okay, in that first recording of the 2 for next week, you're not going to hear me talking about parts of the brain. Okay, we're going to go to a higher level and think about how past experience, how, for example, expectations influence how we interpret and make sense of incoming environmental stimuli. Okay, and there's some pretty memorable examples embedded within that section on perception. Again, our focus this morning, however, is going to be on sensation. So we're going to basically build the foundation for a discussion about sensation initially, and then we're going to dig through most closely your visual and your auditory systems. And as I'm going to tell you, I'm going to leave the other sensory systems for you to take care of in your reading in the textbook. Okay, and I'll explain why in just a bit. Okay. At a basic kind of general level, do you have a sense here of how sensation is different from perception? Hopefully, with what I've given you thus far, that makes some sense. All right, I'm going to begin with one of these pre-teaching, post-teaching little polling questions where I ask you something that maybe you know something about, maybe you don't. I'm not going to tell you the right or wrong answer yet, but then I'm going to teach you some stuff, and we'll come back to this question in another 15 minutes or so. So let's go to the question here. And just give me a number for your answer in the chat box after you read the item here. I'll give you guys a minute to do that. All right, we have an interesting social psychological phenomenon going on. Lots of people saying B, that it's going to be 2 teaspoons the second time around. Matthew and Omar think it might be 1. Anybody want to try 4 or 5 as their guess? So we've got 5 teaspoons in it, and when we add 1, we notice that it has gotten sweeter. What if there's already 10 teaspoons in it? How much would we need to add to notice that it got sweeter in that scenario? Okay, so we've got some variability in terms of people's guesses at this point. We're going to come back to this after I lay the foundation for it with a discussion of something called a just noticeable difference, or a related concept called Weber's Law. So that's what this is going to relate to. I will come back to it in a bit, and I pretty much guarantee you're going to get a question regarding just noticeable differences in Weber's Law when test number 2 rolls around. All right. So let's lay the foundation here for this discussion by first introducing the term psychophysics. It's the subfield within psychology that sensation and perception fits into. It's the study of the relationships between stimuli from our environment, including things like the intensity of those stimuli, for example, and how we psychologically experience them. Okay, so basically I'd say psychophysics, or to summarize this equals research on sensation and perception. So if I do research in sensation and perception, I could technically say I am a psychophysicist. Okay, that's my area of expertise. There are 2 key concepts that we have to get our head around here so that we can use these concepts as we go forward. The 2 key concepts are that of an absolute threshold and that of a just noticeable difference. Not overwhelmingly difficult, and I'll do a number of examples so you guys will have a good sense of how these things work. An absolute threshold, it says here, is the minimum stimulation needed to detect a particular stimulus 50% of the time. The minimum stimulation needed to detect a particular stimulus 50% of the time. So this is a change from nothing to something. What do I mean by a change from nothing? Well, let's imagine that I had you in a completely darkened room, and I had a dimmer switch on the wall that had some numbers that indicate how bright the light is getting. Let's say it goes from 0 to 100, okay? Your absolute threshold for noticing that the light is being turned on, that there's light now when there wasn't light before, is an absolute threshold. It's a change from no stimulus at all, okay? To give you another scenario for an absolute threshold. If you're sitting in your house or your apartment and a skunk walks by outside, when you first notice the presence of that skunky smell, that would represent your absolute threshold for smell, right? It's a change from there was nothing. There was no sound, there was no smell, there was no taste, there was no touch, there was nothing to see, right? And then there was something that became visible or able to be heard, etc. That's an absolute threshold. And I've got some concrete examples of these built in for you here on this next slide. Okay, so here are some absolute thresholds for different senses in case you're curious. Our absolute threshold for touch is the falling of a bee's wing on your cheek. That's the minimum amount of tactile input that is necessary for you to be able to notice that something is going on. For hearing, if you had one of those analog clocks across the room in a completely soundproof room, about 20 feet away from you, you would be able to hear that, okay? If there was no perfume in the room and I dropped 1 drop of perfume in a 6-room apartment, you might be able to notice that, okay? That change from nothing. Vision, a candle flame seen from 30 miles away on a clear, dark night. This taste one, I think, makes a lot of sense. If I have 2 2-gallon jugs of water, one of them has sugar in it and one doesn't, you'll be able to notice at least 50% of the time or more that the jug with water and with the sugar in the water tastes sweeter than the one that doesn't have any sugar in it, okay? So again, absolute thresholds are about noticing something when previously there was nothing, right? So again, I like to keep in my mind here, this absolute threshold is a change from nothing, okay? Nothing was there and now something is noticeable. So if I had a stereo speaker and I turned up the sound from 0 to 1 to 2 to 3 to 4. And when it hit 4, that's when you first heard it. That would be your absolute threshold for hearing, okay? Does that make sense? Questions about absolute thresholds? It's a change regarding some kind of sensory input from there being nothing there to there being something there, right? And there's some individual variability in those absolute thresholds, right? I remember vividly when my wife was pregnant with one of the kids, apparently there's some evidence on this, that the pregnant moms, like they have like this superhuman olfactory system. And the skunk example I used earlier, I used on purpose because we live where there's a sort of a canyon behind us, and sometimes skunks are wandering through there. She would notice the skunk smell, and then like 20, 30, 40, 50 seconds later, then like, oh yeah, I notice it now too, right? My delayed reaction to that smell or sensing of that smell represents that I had a higher threshold, right? I needed more skunk smell to notice it than she did, right? Some individual variability there in those thresholds. What are J&Ds? Well, the term basically defines itself. It's a just noticeable difference. It's the minimum difference between two stimuli that's required for detection 50% of the time. So what's key here? What's key here is we're talking about a difference between two stimuli. So what we're really discussing here with a J&D is what? It's a change from something to either more or less of that something. And I will play with this to make it so that you can actually read it. Okay? To change from something to either more or less of that something. So something is there, and now I notice that there's more of it, or maybe that there's less of it. It's also known as a difference threshold, right? So here's the idea. Let's pretend that I'm sitting in my apartment by myself listening to music, and I'm just going to make up a number. Let's say that I've got this stereo turned up to 10, and my roommate goes, I'm going to check what your J&D is for increases in volume of the music here. And he or she starts turning the music louder and louder and louder, 1 unit at a time. And let's pretend that what it takes for me to notice a change is an increase, I don't know, let's say from 10 to 14. Or conversely, if it was a decrease, it would be from 10 down to 6, okay? If we do the math here, an increase from 10 to 14 is a 40% increase in the volume of that music, right? From 10 to 14, how do I get a 40% increase? Well, the unit of increase is 4 units over a baseline of 10. So it took a 40% increase in the sound for me to notice that it got louder, okay? Or it took a 40% decrease to notice that it got softer, okay? This is an example of Weber's law that I'm setting up, because it turns out that J&Ds are proportional to the size of the original stimulus. How much change is required on the stereo volume depends on where I started that volume at in the first place. So let's, instead of 10, let's say I'm having a rocking party and the music is at 30. And I told you that the percentage increase required for you to notice that it got louder was a 40% increase. So my question for you now is, to what volume number would it need to go if you needed a 40% increase from 30 to notice that the volume got louder? So what's a 40% increase from 30? You didn't think there was going to be any math today. It is not 70. That's more than 100% increase. The question basically is, what's 40% of 30? Or what's 30 times 0.4? Yeah, Matthew's got it. It's 42. So we're going to go up to 42. Or if you want to go in the other direction, it would be a 12-unit decrease from 30 if the music was turned down because the neighbors were getting annoyed. We would go down to 18. Okay? So this is what Weber's law says. J&Ds are proportional to the size of the original stimulus. How much louder or brighter or heavier or smellier something needs to be depends on what you started at, right? So if we go back to the light example, let's say the light is turned on and it's at a 50. And we know that in that case, let's say we're going to make up a number and say it's a 10% increase for noticing a change for you in light intensity. Well, a 10% increase from 50 on the knob would mean you'd have to go up to 55 to say, oh, it got brighter. Or a 10% decrease from 50 would be 5 units down from 50. You would have to go down to 45 for you to notice that it got dimmer in terms of the light. So no matter what the stimulus is, it could be sound or light or whatever, we have proportionality dictating how much change is necessary for me to notice that something has in fact changed. That's Weber's law in action. I guarantee you, ask one of our SI leaders who's logged in right now, if I'm going to ask you a question about Weber's law, I'm going to give you an example like this. Yes, I'm going to. They'll tell you that I certainly will. And they'll practice that with you in supplemental instruction sessions. Let me stop there for a second. Questions about either absolute thresholds or just noticeable differences. If you want to tie these two ideas together, I'll suggest this. If it doesn't make sense to you, you can ignore it. I would suggest to you that an absolute threshold is at J and D from 0. Think about that. Isn't that really what an absolute threshold is? It's the just noticeable change from nothing at all to saying, yes, there's something, right? Nothing to something, whereas J and Ds are about something to either something more or something less. Does that make sense? So this idea of an absolute threshold being a J and D from 0 helps you to tie this together. Great. That's the way I think about it. But sometimes when I suggest that, I see students sort of scratching their head saying, I don't really get that. Any questions on absolute thresholds or just noticeable differences? All this is in the textbook as well. Read it, go through the examples in there, and you should be able to easily get your head around this. So let's go back to the question that we started with. See what you guys think now. How much sugar are we going to need to add here? Now almost everybody's going with B. It's going to be 2 teaspoons. Why? How'd you get there? So it's 1/5. It's a 20% increase, right? So we started with 5 and we noticed a 1 unit increase. So that's 1/5 or 20%. So what's 20% of 10? It's 2, right? So we had to go 2 units of sugar input there because we've got 10 teaspoons in there already versus before we only had 5. Okay. Yep, 1/5 of 10 plus the 10 that you started with. If you get your order of operations right, Joseph, you're in good shape, right? So it's going to be 2 plus 10. It would be 12 total. Questions on that at all? A lot of you guys actually had a pretty decent first stab at that. And if you didn't, and you had C or D as your choice, do you see now why it's B? It's the 20% increase. So what's 20% of 10? That's just 2 more. All right, I'm not going to beat that into the ground if you guys got your head around it. So here's the deal. As I alluded to earlier, I am going to, in my work with you this morning, focus on vision and hearing. Why? What's the deal here? Well, trust me, if I spent this entire session going through vision and hearing and smell and taste and touch in exactly the same way, and I described the hardware that's involved, and I talked about receptor cells and transduction for all of these, by the time we were done, you'd want to stick a fork in your eye. So rather than having you stick a fork in your eye, what I decided to do in this part of the course is to teach you about vision and hearing and give you a framework for understanding those 2 senses. And then I just basically assign to you the reading on smell and taste and the somatosenses, which includes touch. So that when you read about smell and taste and touch, you can say, okay, what were the receptor cells for that sense? Where are they located? How can I take the framework that he gave me in the lecture and map it onto what I'm reading and trying to understand here in the text? So that's your job in this part on sensation, is to read those remaining senses in a way that makes what you extract from that content analogous to what I'm doing with you guys this morning. So we will talk about vision and hearing. Okay, taste and smell, I'm going to suggest right here are together referred to as the chemical senses. So let me get that typed in there for you. These are the chemical senses because in contrast with vision and hearing, which have receptors that are sensitive to forms of energy, right? Vision is responsive to electromagnetic energy. Hearing is responsive to sound waves. Smell and taste have receptors that are responsive to chemical molecules rather than to some form of energy, okay? You probably learned the five senses as seeing, hearing, smelling, tasting, and touching. We subsume touching under the somatosenses. Another little root for you here. Somato always means body, right? So this is body senses. Well, one of your body senses is a sense of touch. So feeling something, pressed on your forearm or feeling something stroking your cheek or whatever the case might be. That's one of our somatosenses. In addition to touch, we have a vestibular sense, which provides information about your body's position, your body's orientation in space. It's related to equilibrium. That is your balance. So if your vestibular sense gets out of whack, you might feel dizzy and fall down. Another somatosense is kinesthesis. Kinesthesis provides information about the positions and movement of muscles and joints. So we're not super interested in that. You will, again, read about touch as you read through the textbook. We will focus, as I said, on vision and hearing. Before I start rolling into a discussion of those two, though, I want to give you two major concepts that I guarantee you need to know for the test, on test number 2, and that are the unifying concepts for all of these sensory systems. The two concepts are going to be receptor cells and transduction. On this next slide, receptor cells and transduction. Hugely important concepts here. So what's the deal? There are specific receptor cells for each sense that stimulate neurons in the CNS. What's the CNS? The central nervous system. That's your brain and your spinal cord. So what we're saying here is this. You have specialized cells in these different sensory systems that take incoming environmental stimuli and convert or translate, or the term down below here is going to be transduce those environmental stimuli into action potentials. So as you read about the other senses beyond vision and hearing, you should be attuned to and looking for a discussion of what the receptor cells are for those other senses. Why? Because the receptor cells are the key players here. The reason they're the key players is that your brain will not directly respond to, for example, light waves. So if I had the back of your skull opened and I shined a flashlight on your visual cortex, which we know is back there in the occipital lobe in the back of your head, okay? You would not say that you see a light as I shine a light on your cortex. Why not? Because the cortex speaks in the language of action potentials, right? So the central nervous system speaks action potentials. That is the language of your central nervous systems, right? So what we need here for the central nervous system to be able to process visual or auditory information is a way to turn the light waves or the sound waves into action potentials. That's what receptor cells do. Okay, so the example that we're going to do for vision and hearing is going to be the receptor cells known as rods and cones. I'll sneak them in here, and we'll say a lot more about them in a bit. So as you're looking at your screen right now and you're seeing the yellow background, the blue letters and the black letters, your rods and cones are transducing. That's what receptor cells do. The sensory input from your computer screen into action potentials. Okay. Why? Why is it so important? Again, because the central nervous system speaks in the form of action potentials, right? Electrical within, chemical between. If you're going to relay visual information from your optic nerve coming out of the back of your eyeball through the thalamus, that information going from the optic nerve to the thalamus has got to be in the form of action potentials. If I open up your brain completely and shine a light on the thalamus, you're not going to say, I see a light. It's got to run through those receptor cells. And the receptor cells for vision are going to be called rods and cones. Okay? So transduction is the other key term here besides receptor cells. When we transduce something, I would give you a couple of synonyms here. We either translate or we convert, right? That's really what's going on here with transduction. We are translating or converting what's coming in from the world, the sights and the sounds and the smells, into action potentials. Again, because the central nervous system speaks in the form of action potentials. So that's its language, if you will. Any questions on these two key ideas of receptor cells and transduction? Again, as you read about the other senses, be looking for information about receptor cells, where they're located, how they do this transduction work. All right, so let's focus in on vision. I'm not going to go into great detail on this slide. It's basically trying to show you that our visual system is attuned to only a very thin band of the full electromagnetic spectrum, okay? We don't see X-rays with our visual system. We don't see radar with our visual system. What we see is a thin band within the full electromagnetic spectrum between about 400 nanometers and about 700 nanometers. On the lower end of that wavelength range, we're talking about purples and blues. On the longer wavelength end of that range, we're talking about oranges and reds. Okay, so our visual system doesn't pick up everything. It picks up visible light to our systems that fall in that range. Again, about 400 to about 700 nanometers. What we need to be able to work with that incoming sensory input from our environment is a bunch of hardware in our eyes that is going to ultimately, again, transduce those light waves, this visible light, into action potential. So what I'm going to do now is review about 6 or 7 major parts of the eye so that, hey, you know what, the next time you go to see your eye doctor and you see that cool poster on his or her wall, you'll be able to know what those different parts of the eye are. You'll be able to impress your eye doctor next time. All right, so let's run through these together. We're going to begin with the cornea. So let's just start labeling these. I'll give you some numbers like I did with the major parts of the brain, right? So we'll make cornea here number 1. What is the cornea? The cornea is a transparent covering over the eye that partly serves to focus light on the back of the eye. So it's basically a transparent covering over your eye. You can see it right here. You can scratch it, and apparently if you scratch your cornea, it's particularly painful. So that's structure number 1. Structures 2 and 3, they go together. It's hard to think about one without the other. So I'm going to type pupil in there, and I'm going to type iris down below here. Pupil and iris. So what's the deal here? The pupil is in charge of controlling the amount of light that enters the eye. Okay, so if it's really dark, your pupil will dilate, that is, become bigger and bigger and bigger to let in whatever ambient light might be available. If it's really bright outside in the San Diego sunshine, your pupil will constrict because there's plenty of light. The size of the pupil is actually controlled by the muscle that surrounds it, and the muscle that surrounds it is the iris. So if you have blue eyes or brown eyes or hazel colored eyes, that color is this. It's muscle. It's the muscle. It's this iris muscle that surrounds the pupil. The pupil is basically a hole in the iris, and the iris either makes that pupil be smaller, that makes that hole be smaller, or makes it be bigger. Okay. So the colored muscle, the iris, surrounds the pupil and helps to control the amount of light that's coming into the eye. 4th structure here is going to be the lens. What is the lens? Well, it's a lens, and what the lens does is it focuses the visual image onto the retina. So you can see the lens here, and it focuses that visual image on the retina, which is this light brown colored structure on the back of the eye. What's interesting about the lens is that the lens is an elastic structure behind the pupil there that gets thinner as you look at objects that are far off in the distance. So if we were sitting in AL 201 today you were in the very back row, to see you in the back row from the front of the classroom, I'd have to have my lens become thinner to focus on that distant object that is you, right? If instead I stop looking at you and I look down at my notes or my cell phone or whatever, okay, as I look at those nearby objects, the lens will get thicker to focus on those nearby objects, okay? The lens tends to thicken and become less flexible as people age. You might notice your moms and dads or aunts and uncles and grandparents doing this kind of thing where they are stretching their arm out to be able to read something. Okay, they're having a hard time with that because of the decreased flexibility in the lens over time. The lens, as I said, focuses the image on the back of the eye here, the sheet of tissue that's about as thick as a piece of paper, known as the retina. So the retina is going to be number 5 on the parade here. And what I'm going to do for retina is I'm actually going to draw a star next to it. So take a guess about why I'm putting a star next to the retina. What do you think is located in the retina that we said is super important as we think about how we convert light waves into action potentials? Yeah, those receptor cells, those rods and cones are located in the retina. So let me just explicitly spell that out here, right? Receptor cells are here, receptor cells. And they are the rods and cones are located right here in the retina, okay? So that makes it a particularly important structure. You're almost certainly going to get some kind of question about the fact that those rods and cones are located there in the retina. All right. So what else is back here? Well, we've got the fovea. The fovea is a point of central focus. And what I'm going to tell you about the fovea, you just put it in your notes here. It's a location that has cones and only cones. There are no rods located at this point known as the fovea. It's our point of central focus, okay? Especially for brightly illuminated situations, it's ideal to get the image in those environments transmitted to or basically shown onto this spot called the fovea. Projected is the word I'm looking for, okay? Structure number 7 is the blind spot down below here. Very often you'll hear this blind spot referred to as the optic disc. The optic disc is a blind spot because it is a location where there are neither rods nor cones. Think about that for a second. If at this location here, there are no rods and there are no cones, well, an image that gets projected there won't be seen by you. Why not? Because the rods and cones are not converting that image or transducing that image into action potentials. Why do we have this blind spot here? Because it's basically the point at which the power cord, if you will, exits the back of the eye, and the power cord is referred to as the optic nerve. So I'm going to call that one number 8 here. This optic nerve, it's about as thick as your pinky, and we've got an optic nerve coming out of the back of your left eye and out of the back of your right eye. And again, at that location where that optic nerve is sort of bundled up and this power cord projects from the back of the eye, we've got this blind spot or optic disc. Okay. By the way, your brain completes patterns that fall onto the blind spot so that you don't walk around aware of like holes in your visual field as you're looking at things in your environment, right? It basically is a situation where you can fill in the blanks, if you will, via some other functioning in your sensory systems here. There's a nice demonstration in the textbook of the blind spot. If you get the book or the ebook screen the correct distance from your eyes, you'll actually be able to have an image that's there disappear because you ultimately are projecting that image onto that blind spot. All right, that's a lot of talking. Let me be quiet for a second. Questions about any of those 8 major parts of the eye: cornea, pupil, iris, lens, retina, fovea, optic disc, and optic nerve. Yeah, the lens's job is basically to focus images onto the retina. So the image out here is a candle. We're going to project it onto the back of the eye where the retina is, because that's where we've got the receptor cells that will do that transduction, that will convert these light waves into action potentials. And I said we use the lens to sort of thin out to see things far away and to thicken when we're looking at things that are nearby. Make sense? Any other questions on the major parts of the eye here, guys? I want to drill down a little bit more then regarding these rods and cones, because they're the stars of the show, again, located in the retina. And what I'm going to add here is a few more details about each. Rods are concentrated in the periphery of the retina. In English, that means we tend to have more rods up in here and more rods in here. We tend to have in the center area here more cones. And in fact, I've already said at the fovea we have cones and only cones. So if the fovea area is like downtown, the rods tend to sort of live out in the suburbs here, if you will, right? So they're more in the periphery. They're specialized for black and white vision, and they're more active when we're in a dimly illuminated environment. Okay, so if you're sitting in the movie theater and Lego Batman, which apparently is awesome, is about to start, as the lights dim, it would be your rods that are becoming more active. In contrast, the cones sort of do the opposite. Oh, by the way, down below here, this what looks like a shag carpet is actually an electron microscope photograph showing all the white rods, and then these little green guys, cones, because, well, they're shaped like cones. What do? Well, they are concentrated in the center of the retina. We know the fovea has cones and only cones. They're specialized for color vision, and they're more active if you're out now leaving the movie theater, walking out into a bright, sunny San Diego afternoon, okay? Got a little mnemonic here for cones. Cones are in the center of the retina, and they're specialized for color vision. Dude, how easy is that, right? All three of them begin with C. Cones, center, color. Any questions about cones? It should be a gimme because it's really, really simple how we spelled it out there. Okay? Any questions about those additional details regarding rods and cones? Remember, where are these guys located? Rods and cones are the receptor cells for vision, and they're located in the retina. Thanks, Francisco. Awesome. I appreciate your paying attention. Good. If you're wondering where this information goes, this is more detail than you need to know. Coming out of the back of the eye, again, we've got the optic nerve, so we can see it here coming out of the left eye and out of the right eye. We saw this little optic chiasm crossover point. We're talking about split brain patients. The visual area of the thalamus relays that visual information on. Again, thalamus does everything other than smell until it gets it back here in the visual cortex in your left occipital lobe and your right occipital lobe. Okay, that's where things ultimately end up, because that's where we've got the cortical structures that are specialized for processing visual information. All right. That's just the way things are built here, Francisco, in terms of cones and only cones. It's a point of central focus. There's probably something about the evolution of vision over time in humans that made it so that these cells tended to be specialized right there. I don't know the whole story or the backstory on why that is. I just know that it's true. And we've got those cones and only cones in the fovea. It's a special point of, especially for bright, colorful images. That's where you'd want to get that image. Okay. In contrast, if it was a dark environment or some black and white image, projecting onto the fovea really wouldn't be the best use of the resources you've got, right? You'd want dim illumination or black and white images to go more along the periphery of the retina. Those brighter and colorful images more towards the center, especially onto the fovea itself. All right, let me ask you a little polling question here, this one. So take a look at this. It's dark in your house and you're struggling to see what time it is without turning on the light. You notice that if you turn your gaze slightly to the side of your watch, you can make out the large numbers. The ability to see these large details in the dark is due to what? Give me an answer and explain why you're choosing that answer. Anybody got one? Yeah, it's rods, right? They're dim illumination. That's exactly what we want to see, right? So in this dimly illuminated environment, we want images being projected more along the edges of the retina. If you're looking at a dark sky at night, right, you want to have that image go to those areas in your retina that are specialized for that dim illumination, those dim settings, as Aeneas has said there as well. Sorry if I didn't say your name right. All right, we've got about 20 minutes left. It's going to take me about 15 minutes to walk through with you guys the auditory system. So let's just do another review of the major structures here, like we did for vision, but now we'll do it for hearing. And now you're seeing, right? Thank God I'm not going to do this for all the senses, right? We're going to do 2 of them. You're going to read about and get your head around the rest of that. All right, so it says here, number 1, the pinna funnels sound waves into the auditory canal, focusing them toward the eardrum. It's actually got 3 structures already in bullet point number 1 there. The pinna is what hangs off the side of your head. The pinna serves to funnel sound waves. So as sound waves are coming in from our environment, what the pinna is doing is gathering them up, right? So you might have even used your hand to extend the pinna, right? You sort of curl your hand around the pinna to make it a bigger funnel, if you will, to gather those sound waves up. So if we're going here through the major structures, pinna would be 1, auditory canal would be 2, and then eardrum would be 3. Okay. What is the eardrum also known as? Well, you might have heard the eardrum referred to as the tympanic membrane. So let me type that fancier term in there. Tympanic membrane is another term for this eardrum, which sits right here. Okay, so again, funneled in by the pinna down the auditory canal. It's basically a roadway, if you will, from the outer ear to the middle ear. Bangs on the eardrum. The 4th structure I'm going to simplify for you because they break it up into hammer, anvil, and stirrup. Let me make this a little bit easier for you and tell you that those 3 bones together, the hammer, the anvil, and the stirrup, are collectively referred to as the ossicles. The ossicles are these tiniest bones in your body. So here they are, hammer, anvil, and stirrup, which actually really looks like a stirrup. And what those bones do is they vibrate and continue to pass along the vibrations that were sent their way via the eardrum. Okay, so it's like a game of operator here where we're sending the message along down the line, right? Ultimately, what happens is the final one of these ossicles, this stirrup, is pressing on a structure known as the cochlea. The cochlea is this structure right here. It looks like a snail. It looks like a cinnamon bun if you're hungry. It looks like a shell. It might even look like, as a Carrie Fisher tribute here, Princess Leia's hair wrapped around and stuck to the side of her head, right? That is known as the cochlea. The cochlea is going to be structure number 5 here. And the cochlea is going to be the structure that I'm going to put a star on. Why am I going to put a star on the cochlea? What's going on there? Somebody tell me in the chat box. Why is the cochlea getting a star? What does it have? It's got the receptor cells. Yep, it's got the receptor cells for hearing now. And I'm going to tell you that the name of those receptor cells located in the cochlea is hair cells. Hair cells do for hearing what the rods and cones did for vision. Okay, so again, the sequence: pinna, down the auditory canal, bang on the eardrum, vibrate the ossicles. The final one of those ossicles, that little stirrup, presses on the oval window. It's a specific location of this cochlea. And what happens is the hair cells are going to be manually stimulated. And it says over here, there's an auditory nerve that carries signals to the auditory cortex in the brain, where sounds are given meaning. So I guess the 6th structure that I should sneak in here is the auditory nerve. Auditory nerve, which is just like the optic nerve was for vision, right? So if this were numbering this, I guess the auditory nerve deserves to get number 6. So the auditory nerve does for hearing what the optic nerve did for hearing, did for vision, right? So I described the optic nerve as kind of the power cord, if you will, coming out of the back of each eye. We've got an auditory nerve, kind of power cord, coming out of the cochlea, both in our left ear and in our right ear. Ultimately, that auditory information, as we're going to see, is going to get routed through the thalamus and then back out to your temporal lobes, basically right in and up from where your ears are, okay? So that's the full sequence here. We come in through the pinna, down the auditory canal, bang on the eardrum, move those ossicles. Ossicles press on the hair cells in the cochlea. The ossicles, press on the cochlea, vibrating those hair cells. And then ultimately the message comes out through the auditory nerve. I want to show you a really nice electron microscope picture of these hair cells so you get a better sense of how this works. So here's the picture on the right from the electron microscope. Here are the hair cells. They look like little hairs sticking up, right? Almost like little blades of grass, if you will, sticking up along this basilar membrane. So here's the stirrup pressing on the oval window of the cochlea. This pink structure here is the basilar membrane. It's this sort of like sand-looking structure over here in this electron microscope picture. And what happens is underneath that basilar membrane, there is a gelatinous substance called endolymph. It's kind of jello. It's like jello. Okay. Now I'm going to ask you a weird question. If I have jello sitting underneath the ground here and I start pressing on this thing, right? If you press on a bowl of jello or you slap or push on a bowl of jello, what is the jello going to do? It's going to jiggle around. That's exactly what happens. Underneath this basilar membrane, there's jiggling, there's moving around, there's wiggling under the ground here, if you will. And now these hair cells are going to start waving. So like picturing, grass blowing in the wind. Well, rather than blowing in the wind, these guys are wiggling around because the floor, if you will, under them is gelatinous. It's wiggling and jiggling around. And that's what physically stimulates these hair cells, okay? So let me go back to this picture here. Let's just read through the text that's built in to see if all this makes sense. And then I'll stop to see if there are questions. Number one, the pinna funnels sound waves into the auditory canal, focusing them toward the eardrum. Number two, vibrations in the eardrum cause the hammer to push the anvil, which moves the stirrup, which presses on the oval window, amplifying those waves. Number three, pressure on the oval window causes fluid in the cochlea, this endolymph jello stuff, to vibrate. That vibrating fluid, number four here in the cochlea, bends those hair cells on the basilar membrane, triggering action potentials. Amen, right? We need action potentials. That is the language of the central nervous system. So action potentials in the auditory nerve have been triggered. And then number five here, the auditory nerve carries signals to the auditory cortex and your temporal lobes where sounds are given meaning. We'll say more about that in a bit, because that's where we sort of transition from the earlier biological sensation to the later, more psychological perception, right? When sounds are being given meaning, and I hear the voice and I know it's my mom and not my brother or my sister, now we're at perception level, right? We moved away from the earlier, more biological sensation that we're talking about here, and we're on to perception, okay? To help you pull this together, rather than having a whole bunch of individual terms and items, I always like to build these tables. You guys know this by now, right? We had that giant action potential table last week. So this table says, name the sense, tell me the name of the receptor cells for that sense, and tell me where those receptor cells are located. So for vision, you know, there are rods and cones and they're located in the retina. In fact, you could expand in this box and say more about rods and cones. You could say that rods are more in the periphery. They're black and white vision, they're dim illumination. You could say cones are in the center. The fovea has cones and only cones. They're color vision, they're bright illumination. Fantastic. What about this auditory system that we're talking about? Well, we've got hair cells. Those are the receptor cells for hearing. They're located in the cochlea. You could even say they get manually stimulated because this basilar membrane sort of wobbles around, if you will. and makes them wave as the ground, if you will, underneath them is jiggling around. Okay, you can add additional cells underneath here when you read the textbook. What's the sense? Okay, now I'm reading about taste. What are the receptor cells? Where are they located? And off you go. Okay, it's a nice way to get connected with each other, different concepts that are similar, right? I was explaining to the 8 o'clock class, I just did this Sunday night in studying with my 6th grader about different tools that meteorologists use to study the weather. There are thermometers and barometers and anemometers and wind vanes. So we made a little table, those 4 things. How do they work? What do they tell us? There's a couple more columns. Now we're pulling together and connecting with each other content that could instead be just a giant list of terms, right? You're going to do better when you build networks that connect these terms with each other, where you see similarities and differences as you study this. All right, so let me give you guys this little simple, hopefully the easiest polling question of the day. Rods and cones are to vision as what are to audition? Yeah, rods and cones are the receptor cells for vision, just like hair cells are the receptor cells for hearing. Awesome. All right, last 10 minutes, I promise. Let me give you one final summary in words and sneak in a couple of extra things in terms of summarizing the sequence here for hearing. Ossicles magnify sound vibrations from the tympanic membrane. In fact, if you want to put step 0, you could say what? The pinna funnels sound waves down the auditory canal. Ossicles magnify sound from the tympanic membrane. All the bold and underlined terms, you should know what they are, right? Hair cells in the cochlea fire action potentials. Again, we love that because the auditory cortex in your temporal lobes of your brain, they speak action potentials. So we need hair cells to do that transduction. They do it in the cochlea, just like rods and cones do for vision in the retina. Sneaking in one new term here called the inferior colliculus. This is a structure in your brain that we ignored in the bio section because we had enough bio that actually helps you localize sound in space. What does that mean? Well, if I localize sound, that means that what I'm doing is I'm figuring out where it's located in relationship to me. Is it in front of me, behind me, to my left or my right? If you've ever been in a car and you hear a siren, you might have even found yourself turning your head to try to figure out where that sound was coming from. Okay? There is an analogous structure actually for vision that, believe it or not, is called the superior colliculus. So if you're a hawk soaring over a canyon looking for a scrumptious animal to eat for lunch, your superior colliculus is helping you figure out where those things are for your visual system. For hearing now, the thalamus is going to distribute frequency information. You're going to read more about this in the textbook, but it turns out that the frequency of sound waves is what determines their pitch. So if I hear a higher pitch sound or a lower pitch sound, those sounds vary in terms of the frequency of the sound waves that are coming out. And then finally, your auditory cortex interprets the sound. This is the point at which we are sort of transitioning away from sensation, and we're starting to move towards perception. Okay, so when we interpret the sound, we might be figuring out if it's a dog versus a cat. Is it my mom versus my brother, right? As we're hearing these things, that higher level work is now moving us into perception, and we're ending up with sort of a mental image, right? I hear barking and I picture a dog. I hear a meow, I picture a cat. Or maybe I hear the roar of a lion and I realize that's like a really big cat, okay? That's happening at the level of the overlying auditory cortex, again, in your temporal lobes. And that's really when we get to perception, right? So your ability to discern the difference between the sound of a dog and the sound of a cat is kind of based on your experience as a listener, right? What you've heard over time and how you've seen connections between those sounds and those different animals in your environment, okay? So this is a really good spot as we see the transition away from sensation and now towards perception. And what I want to do in the last 3 or 4 minutes here is just explain to you what you're going to hear as you start listening to the first of those 2 video recordings that you'll watch next week, because again, we won't have a face-to-face class on Tuesday or a live online session on Thursday. You've got those 2 videos to watch. So what's going to happen as you move into that? Well, you're going to be learning about perception. Remember what we said already a couple times today was this perception was what? It was later and it was more psychological. Let's keep that in mind as we move into that first recording. So perception is the organization and interpretation of sensory stimuli by the brain. I really like the interpretation part of this, right? It's how we sort of figure stuff out, how we make sense of new things based on our previous experience, right? How we interpret and understand, you know, similarities and differences. So that's a jaguar. It's not the same as a cat, a house cat. It's not the same as a lion, but it's similar enough, and I sort of get my head around that and interpret and understand that at this perceptual level. Okay, a little bit more to introduce perception here. Perception includes the processing, organization, and again, interpretation of these sensory signals. So now we're away from the biology and we're more on the psychology. It ultimately results in an internal representation of these environmental stimuli. And the word that always comes to mind, or the phrase that always comes to mind when I see internal representation, is that of a mental image, right? So as you hear your dad's voice coming through the speaker on your cell phone, you picture that guy, right? As you hear some sound in your environment, right, you picture what's going on there, right? This is an internal representation. So if you hear the roar of a lion in a sound file on your computer, you sort of picture like this big cat, you know, might have a large mane, a huge head, and it's a different mental image from that if you hear the meow of a kitten, okay? So this mental image idea, I think, is a good one to sort of help you see how when we move to perception, we've gone beyond rods and cones and transduction and action potentials and sort of the biological hardware. And now we're going to more subtle, more psychological levels of processing of this incoming information from our environment. All right. So again, your job is going to be to check out these recordings. You're going to jump into perception next. That's this recording right here. If you click on it, it'll just start playing and you'll have a grand old time. You can listen to it in chunks. You don't need to listen to the full, whatever it is here, an hour and 11 minutes at once. When you're done with that, later in the week, next week, maybe Wednesday or Thursday, maybe you put it off till Friday, you'll listen to the section on consciousness. That's where you'll be learning about sleep and dreams and drugs and alcohol. Okay? That's the lay of the land going forward. It's everything I've got for you today on sensation. You're going to move into perception next week. Any final questions on anything that we've talked about today? Cool, because my brain is pretty much fried now. Once I talk for 150 minutes, almost straight between these 2 sections, I'm pretty much brain dead. So what's the lay of the land? I have online office hours today from 11 to 12, so click on the office hours button on Blackboard if you need to touch base with me. If you want to review your test, remember you can do that with the TAs. So I recommend that you email them if you can before you go see them. It's on the button here that says TA office hours. They're really great TAs. You guys are really lucky to have the 2 Elizabeths and Noelle and Sage helping you guys out. The good news is Sage is also involved with helping with the research participation requirement. I know she sent you guys an email about some of that the other day, so she's a resource for you in that regard as well. That's everything I've got. Any final questions for me before we wrap up? So you guys will see me again face-to-face on Tuesday the 28th. So that's 12 days from now. Next week, you view these 2 recordings. Again, off of the announcements. It's in your email as well, but I know you don't read email because email is for old people. Okay, but there they are right there for you in those announcements. When we get together then on the 28th of February, that's when we'll be moving into the section on learning. And as I alluded to earlier, that's going to be a major area of emphasis on test number 2. So we'll do learning on Tuesday the 28th and Thursday the 2nd of March as we move into March already, believe it or not. That's it, guys. I'm going to stop the sharing, stop the recording. Have a great weekend, and I'll see you when I get back in town and we get back together again on the 28th. Thanks, everybody. Thanks, Francisco. You too.